Welcome to my channel Science for Daily Life. Today we will see how the calculus will help us to calculate some of the important things that we are coming in our daily life. See, for example, this time we have taken as a conical vessel. So this is what the conical vessel which is marked in the red color. Okay, whose height is a capital H and its base radius is R. Here, I just want to know what is the volume of this cone and what is the surface area of the cone. Both of the things are it's possible to calculate using the calculus. Now we'll see how that we are calculating. Everybody, we know that volume of the vessel or conical vessel for that matter. Conical vessel is equal to 1 by 3 pi r square h. We'll see how to derive this formula using the calculus. Say this vessel is being kept in this particular orientation. I've taken this is the radial direction axis and this is the I direction axis H. And I have taken at a particular distance from the apex. I kept that vessel upside down. So apex is kept in the bottom. So from here, height H I have taken. At that particular H, a small pH, an element is considered infinitesimally small element is considered dh. Width is dh. Okay, so at that particular point, the radius r, the green color, what I mentioned here, r, small r, this can be easily calculated based on that. What is that equilateral triangle? This triangle property we can easily calculate. R is equal to r multiplied by h divided by h. This is because of the property of the similar triangles. Okay, so r divided by small h should be equal to capital R divided by the capital H. Using that formula, this is a rule actually. Small r divided by small h should be equal to r divided by h. So from this equation, I can derive that r is equal to this. So volume of this small element, the small string, I can calculate easily as a cylinder because the dh is an infinitesimally small element, so that the variation of radius small r within that small element can be considered as what is that negligible. That is that r is constant throughout this small infinitesimal volume. So this volume is equal to pi into r square into dph. That is what is the volume of this small element. Now we will replace this r with that formula given out. So with this you can get it pi into r square become r square into h square by h square into 2. This is what that small volume d of volume. Or in simply I write that d. Okay, this is very important formula. Now, if you want the volume of this code, it's right now it's very easy. From now onwards, it's easy. The total volume of the cone is nothing but equal to integral of dv. You have to integrate it h from 0 to capital H. So this is nothing but pi r square by h square. These are all constants, so that I can take it out. Integral of 0 to capital H square h equal to pi r square by multiplied by h cube by p, and definite integral you have to apply the limit, so it's going to be pi r square by h square multiplied by h cube minus 0 by 3. So finally I can write that simplified. So my volume is equal to 1 by 3 pi r square is derived. Is that only thing that we have the what is that relationship? No. Apart from that, we have a very important what is that application also for the calculus. Say, for example, you are filling this small or any big what is that conical vessel with a incoming water. Say, for example, you say this is a small what is that cone that I'm having. I'm filling it with the water with a fixed rate. Say, for example, dV by dt, that is rate of volume, say 10 liters per second, is equal to 0.01 meter cube per second. Now, I want to know at what rate that height is increasing within this. See, I know volume is equal to, at any point of time, 1 by 3 pi r square into h. But this is suppose h at that point r that we know already. So that can be replaced at 1 by 3 pi multiplied by r into h square by square into h is equal to 1 by 3 pi r by h square into h small h cube. Now this is a very important equation for calculating the changes in the height if we fill the conical vessel using a tap or some flow you at a constant volume rate, that is 10 liters per second or 0.01 meter cube per second. Now differentiate this. dV by dt is equal to 1 by 3 pi r by h square. These are all constant. Multiplied by 3h square. So this 3 and 3 get cancelled and you will get a new formula for connecting the volume flow rate and the rate of increase the height. dV by is equal to pi into r multiplied by h divided by h whole square. Sorry, here r square issue. Everywhere r square. Pi r square into h by h whole square into dh by dt. Sorry, missing here dh by dt because I am differentiating the volume with respect to a third variable time. So dV by dt is equal to 1 by 3 pi r square by h square into 3h square into dh by dt. What I am interested in is dh by dt. Okay, so dh by dt is equal to dV by dt divided by 1 by pi r square into 1 by h whole square. So this is nothing but dV by dt into some constant where k is equal to 1 by pi r square into 1 by say x square where x is equal to h by h because the rate of change of height also depends on at what height that you want to calculate. This value is varying from 0 to 1. If the value of x is equal to 0 means it is the bottommost portion. And if value of 1 is equal to the top, that is the conical vessel is completely filled. Okay, so now we'll see interpret some of the interprets. Okay, now I am getting a formula like this: dh by dt is equal to dv by dt into k. K is nothing but 1 by pi r square divided by 1 by x square. Suppose if x equal to 0, that means your dh by dt equal to infinity. What does it mean? When you start pouring the water into it, the rate at which it increasing the height at the lowermost portion, that is where the What is that? Height is almost zero. There it is increasing at enormous speed at this point, the height. Okay, so that is where your increment is very high. Once x is reached the one value of 1, we have dh by dt equal to k into dv. This is topmost. So this is the slowest increment speed and this is the maximum increment speed. At any point of time, if you want to calculate what is the rate of increase of the tide, at what speed the tide is increasing, you can use this particular formula. So you can easily calculate. The similar fashion, you can also try the surface area calculation and at what speed the surface area, I mean, you are increasing the surface area by brushing something will increase that what is that A and height of coverage, rate at which the height of coverage is increasing. That is also quite possible using the calculus. I hope this type of calculus will definitely help you and will make you to enjoy to calculate and to solve so many problems that we are encountering in our day-to-day life. Thank you very much for the patient listening. Thank you.